Well, I can safely say that 2022 was not a massive improvement on previous years. An improvement, yes, but not a massive one. At times it seemed we were just swapping out one horseman of the apocalypse for another. Still, if I can say one thing for 2022, unlike last year, where I literally had to go begging for ideas for a top 10, this year overwhelmed me with possible inclusions. I could easily have made a top 20, and with the James Webb finally operational, and the Vera Rubin coming online next year, I'm not planning to beg in the near future. One thing I should say before we start. No, we did not in fact achieve sustainable fusion this year. Yes, the US National Ignition Facility did generate 3 megajoules of power for 2 megajoules of energy, but the total energy required to set up the experiment was 300 megajoules. It's a good sign, but we've a ways to go yet. So, with hope for the future of our currently dazed planet, let us depart and see what our universe revealed to us in 2022. I'd like to begin, if I may, with an honorable mention. In October, astronomers around the world observed the single brightest light ever seen. A long-duration, about 10 hours, gamma-ray burst in the constellation Sagitta, not to be confused with Sagittarius. So energetic was it that every photon it released carried 18 tera-electron volts of energy, tens of thousands of times more powerful than a typical gamma-ray burst, and more than generated by the far heavier particles at the Large Hadron Collider. The blast was so intense, it could briefly be seen by amateur astronomers. It even affected long-range radio communications and registered with lightning detectors. The source of this eruption is believed to have been a massive supernova about 2.4 billion light-years from Earth. That makes it the closest high-energy gamma-ray burst ever seen. And it was that combination of proximity and power that led to the burst's intensity. Given this proximity, the burst can be analyzed far more minutely than usual, which may give us more information on how the children of massive supernovae, black holes, form. As it passed through galactic clouds, the burst created light echoes that allowed us to measure their distance. The only reason I cannot place this in the top 10 is that, like all of its kind, it is a one-time event, and thus not subject to repeat investigation. Ce n'est pas la fin du monde. Have I ever mentioned that I hate dark matter? Not as a hypothesis. It makes perfect sense in light of observations. I hate it personally, as if it were a sentient being, slouching smugly in the shadows, daring us sniveling apes to catch it. I seldom bring it up because doing so tends to raise the hackles of anyone even remotely astronomically inclined, let alone professionally so. And I get why. Armchair physicists like myself often berate professionals for adhering to it, as if it were a fantasy concocted to spare their academic blushes. It is not. Dark matter is a completely valid scientific hypothesis, and until we have enough evidence, we must adhere to it as the default. I'm not about to criticize anyone, least of all scientists, for doing so. When test after test appears to confirm its existence, even across multiple lines of evidence, you're stuck. At least until either you find it, or the next Einstein comes along. But speaking strictly personally, I have always entertained the somewhat spiteful assertion that dark matter does not exist, and that the fault lies in our understanding of gravity. Ideas along these lines have existed since dark matter was proposed, most of them falling under the umbrella of MOND, or modified Newtonian dynamics. The argument goes that just as Newtonian gravity fails in close proximity to large gravitational fields, so it also fails at galactic scales, and that, in the case of objects with very low accelerations, such as stars in the outer rims of galaxies, gravity only decreases linearly with distance, rather than geometrically as with standard gravity. If that seems arbitrary and ad hoc to you, that's because it is, and so far only solves the mystery it was designed to solve, the rapid rotation of the outer regions of galaxy. for the motions of galactic clusters and superclusters, dark matter still reigns. But MOND, or more accurately, an Einstein-friendly variant called equal, can be tested, as it leaves very different fingerprints on a galaxy from dark matter. And in December, Kyu-Hyun Chai, an astronomer at Sejong University in Korea, apparently found one of those fingerprints. One of the differences between equal and dark matter is that dark matter predicts the arc of motion in a galaxy as smooth, in line with understanding of gravity. But equal, due to its peculiar predicted dynamics, should produce a tiny kink in the gravitational curve. This kink is too small to be seen in a single galaxy, but after surveying 152 galaxies in the Spitzer database, Chai observed just such a kink emerging from the data. In October, a team at the University of Bonn conducted a study of tidal tails in open star clusters, the gradually dissipating birth clutches of young stars. Tidal tails are a rather beautiful outcome of Newtonian gravity at the highest level. Just as the moon raises bulges on both sides of the Earth, causing the tides, so gravity pulls the ends of a galactic cluster into sweeping arcs of gas and stars. Newton predicts that the distribution of stars in either tail should be random, but after carefully mapping the direction, velocity, and age of the stars within 5 nearby open clusters, a feat impossible before Gaia, they found that stars in the forward tail outnumber stars in the rear tail. This result contradicts Newtonian predictions. However, it is in line with MOND, which suggests that stars more easily fall into the rear tail than the forward. Enticingly, MOND also suggested that open clusters should dissipate far more quickly than suggested by Newtonian mechanics, which is in line with other observations. So it seems that, on the galactic scale at least, MOND still holds up. This raises the frankly terrifying prospect that dark matter may have several different causes, but then the universe has never not been exasperating. But if dark matter does exist, at least we know one thing it is not. Our old pal, primordial black holes. For those who missed my video on whether Planet 9 was a black hole, a primordial black hole is a black hole that formed from the direct collapse of a cloud of gas, in much the same way a star does, a fraction of a second after the Big Bang, when pressures were high enough. We don't actually have any evidence for the existence of primordial black holes, but they have been suggested repeatedly as dark matter candidates, which makes sense, as if they exist, they would be quite literally everywhere. Which makes the fact that we haven't found them somewhat odd. After all, it's not like black holes are particularly stealthy. They bend and warp starlight around them in very noticeable ways. If they were everywhere, we should have found at least one by now. In December, a team of astronomers in Italy and Switzerland tried to determine if primordial black holes were hiding from our gaze by huddling together. If they were strongly clustered, then their effects, such as gravitational waves and microlensing, would be less noticeable. There is no better place to hunt for hidden prey than a forest. In this case, the Lyman alpha forest, a tangle of absorption lines and spectra from distant objects created by light passing through hydrogen, as you can imagine, a not uncommon event in the universe. While a pain to steer through, the Lyman alpha forest can be used to measure the density of matter, even dark matter, at cosmological distances. The team found that to conform to their data, primordial black holes would have to be weakly clustered, rather than strongly. This showed that, if they were of stellar mass, primordial black holes made poor dark matter candidates. Dark matter, you cad. You cannot hide in your oubliette forever. One day, we will pull aside the curtain and see you for what you are, even if you are nothing. That day, for me, cannot come soon enough. Getting in touch with Mum. We like to think of our home planet as our mother. The more astronomically minded might grant that honor to our home star. But our home galaxy doesn't receive anything like that level of affection. This is understandable. Unlike our planet and star, our galaxy doesn't move on human timescales. By the time we swing halfway around the galactic clock, new orders of animal life will have evolved. Also, we didn't even know she existed until the 1920s, and what with us being trapped within her, we've had to guess what she actually looks like. Less a mother, really, than a long-lost relative we've only communicated with by letter. But, thanks to recent innovations like the Gaia probe, which precisely map the positions and motions of over 1 billion stars in our galaxy, we're finally getting to grips with our distant matriarch. For instance, we know that, rather than birthing children, she brings children into her embrace, each one adding its essence to her ever-evolving complexity. If that strikes you as Saturn swallowing his offspring, you should know that in 5 billion years, she will finally give herself up to the Andromeda Galaxy, a larger paramour currently 2 million light-years away, but advancing relentlessly. And in January, with a combination of Gaia data and a new survey by the Multiple Mirror Telescope in Arizona, a team at the Harvard Center for Astrophysics attempted to reconstruct our galaxy's last major collision. This prodigal child, named, rather frustratingly, either the Gaia Sausage, Gaia Enceladus, or Gaia Sausage Enceladus, abbreviated to GSE, just make up your frickin' minds, was inferred from a swathe of stars about 20 kiloparsecs from the galactic center, all with high eccentricities, as well as 8 globular clusters in a similar vein to detecting asteroid families. This final major collision occurred between 8 and 11 billion years ago and increased our galaxy's mass by about 1/30th. For comparison, the Sagittarius dwarf, the galaxy currently knocking on Mum's door, will only increase her mass by a 4,000th. Using computer models programmed with the star's motions, ages, and compositions, the team concluded that the sausage had struck her from the direction against her rotation, and ultimately contributed to up to half the matter in her halo. In March, a team at the Max Planck Institute for Astronomy in Heidelberg combined data from Gaia with the Lamos spectroscopic survey to obtain both the locations and compositions of 250,000 stars, and from them determine their ages. To aid in this, they focused on subgiant stars, stars just on the edge of red gianthood, a phase of life which, in stellar terms, lasts only a very short time, allowing their ages to be fixed more easily. While the ages of stars cannot be determined with absolute certainty, by combining their metallicity, the amount of material heavier than hydrogen and helium in their atmospheres, with their brightness, measured against models of stellar evolution, the best estimate can be obtained. Suddenly, the Aussie team had a time map of the Milky Way. This revealed a wild and strange history for our mom. The Milky Way can be roughly divided into 3 distinct regions: the bulge, which envelops the galactic center, the halo, which enshrouds the entire galaxy and contains its oldest stars, and the disk, the most familiar part of the galaxy, which we see every night and where we happen to reside. But the disk can be further subdivided into the thin disk, where we are, and the thick disk, which surrounds the thin disk like a cloud, containing just 10% of the galaxy's mass. Hypotheses for thick disk formation have generally assumed that it formed after the thin disk, but the Australian team's survey suggested, surprisingly, that it formed first, less than 1 billion years after the Big Bang. The majority of its stars were formed 2 billion years later, triggered by the arrival of the sausage. The thin disk only formed after that point, in the second phase of the galaxy's evolution. The thick disk would continue to form until its gas was exhausted 7 billion years ago. In my 2021 video, I mentioned that despite all the freaks we have seen in our 30 years of exoplanet hunting, planets orbiting pulsars, gas giants orbiting white dwarfs, Jupiter-sized planets in roasting 4-day orbits, our solar system, when viewed objectively, represented about 14% of solar systems in the galaxy, and so was relatively normal. This year, a similar study of the Sloan Digital Sky Survey drew the same conclusion for our galaxy. In December, an international team of scientists from the US, the UK, and Chile sifted through 10,000 galaxies to find those most like our own. Of the 138 galaxies selected, 56, or about 0.5% of the original 10,000, were our galactic twin. 1 in 200 may not seem like a lot, but it adds up to 1 billion galaxies like our own in the observable universe. With the aid of computer modeling, the team considered that what distinguishes galaxies like our own is their long, slow periods of star formation within their outer regions, while the innermost regions see an initial burst of star formation before quieting down later, birthing new stars from the gas cast off from the outer regions. A second category of Milky Way-like galaxies, comprising another 55 of the 138, were those whose star formation was lazy and continuous throughout, without the quick burn at the core. A final and more freakish group, comprising just 27 of the 138, were dubbed centrally quenched, as they showed no current star formation in their cores, suggesting they were not receiving the inflow of gas from the outer regions a la Milky Way-type galaxies. The team speculated that these galaxies may represent our galaxy's future. Every mother fears growing old, but our galaxy still has some vim in her yet. She'll get a nice ripple of new star birth when she finally ties the knot with Andromeda, and isn't expected to run out of gas for at least 1 trillion years. So don't start asking her about retirement plans. Welcome to the wild. We used to think we had it figured out. It only took 200 years, but we had a solid vision of how our solar system formed. None of this crazy capture nonsense. Our planets were born of the same mother as our sun, a cloud of gas and dust, set into motion by a supernova. As it span, its furthest reaches flattened out like a pizza tossed in the air, while the infant sun blasted it with its birth cries. Over time, dust within the disk began to accrete, first into lumps, then into rocks, then into mountains, then into worlds. The first worlds to form feasted on the swirling abundance, growing so large that they cloaked themselves in the surrounding gas, evolving into mini versions of the sun. This abundance was due to their location, far enough from the sun so that volatile substances such as water, ammonia, and methane would remain solid. Farther in, cooked by the raging monster at the center, the protoplanets could only form of relatively rare materials like iron and silica, and so remain small. And that was it, more or less. Obviously, the inner planets had to get their water, but comets could take care of that. And then we started finding planets around other stars. Suddenly, gas giants were roasting in the glare of their parent stars, where they never could have grown, or swinging in wild orbits at near cosmic distances. Planets were whirling around pulsars, when they should have been rent asunder by the preceding supernova. Our ideas of planetary formation had to be completely redrafted. From the staid coalescence of old, our solar system's infancy now has planets obliterating each other, and gas giants dancing around each other like baleadoras. I mean, if everyone else was doing it. 2022 thankfully saw many instances of our universe playing wild style with the Legos again. Case in point, in February, a team at the Catholic University of Leuven found striking evidence that planet formation is tied not only to star birth, but star death. When a star like our Sun dies, it will not be afforded the glitziness of a supernova. Instead, it will simply cast off its outer layers in a great expanding sphere of gas, leaving behind a white dwarf. Early astronomers, seeing this sphere's resemblance to a planet's disk, called it a planetary nebula, a name that is, in this case, doubly confusing. You see, when a planetary nebula is part of a binary star system, the other star's gravity can shape it from a sphere into a flat spinning disk, not unlike a protoplanetary disk around a nascent star. In fact, not unlike it at all, because the Leuven team found that 10% of these swirling spirals exhibit gaps exactly like those seen in forming solar systems. While it is possible that these gaps are not caused by unseen planets, they are still the most likely culprits. It is interesting to ponder. If the widowed star survives long enough, could it one day warm those planets as they circle around its dead companion? Perhaps enough to beget life? Or even mind? Would such minds even dream of the world theirs had once been? Another rewrite of the planet formation textbook occurred in May, thanks to the efforts of the B-star Exoplanet Abundance Study, or BEAST. As its name suggests, the beast's goal was to see how many planets occur around B-type stars. B-type stars are hot, bright, blue, raging monsters whose masses range up to 16 times that of the Sun, and whose surface temperatures top 30,000 K. The ferocity of such stars is thought to inhibit star formation, as their monstrous solar winds blast through any accreting material. Stars smaller than B-type, even massive A-type stars, have been shown to have planets in plenty, but around B-types, the cupboard is sparse. The beast was inaugurated to determine if the relative paucity of planets around B-type stars was due to their stellar winds disrupting formation, or simply selection bias due to most detection methods favoring planets with smaller orbits. And this year, it uncovered a true curio, the first planetary system around a star predicted to end its life in a supernova. The system comprises at least one super-Jupiter-sized planet, another as yet unconfirmed, in a distant orbit around a naked-eye star, Mu-2 Scorpii. Under most circumstances, such detections would be impossible. Most forms of exoplanet detection rely on the planet having an orbital period short enough to be noticed. The only way this planet could have been seen was directly. Basically, they took a picture of it. Thankfully, it was bright enough and far enough away from its star, which was in turn close enough to Earth, for the image to resolve. And when I call the planet's orbit distant, I'm not kidding. Its semi-major axis is 242 AU, and its orbital period is estimated at 1,251 years, the sort of orbit that in our solar system would belong to a distant detached object like Sedna. But this was no Sedna. Its mass was 14.4 times Jupiter's, verging on brown dwarfhood. So how could it have formed? Its size suggests it didn't form like a star, from the collapse of a nebula. But could it have formed planet-style, from accretion? One possibility, put forward by researchers at the University of Sheffield in September, is straight-up theft. Capture as a formation hypothesis for solar systems is generally looked down upon as unlikely, which is true for a middle-aged star like the Sun. But stars are born in clutches, and it is entirely possible, given about 10 million years, for one to swipe a planet from one of its siblings, while, as it were, still in the womb. But for the initial beast team, the answer is likely a lot simpler. We've been thinking too small. Yes, B-type stars would have annihilated any planets forming at the mundane distances of our solar system, but Mu-2 Scorpii is massive enough, at 9 solar masses, to have gathered a protoplanetary disk that not only extended to the planet's orbit, but contained material sufficient to have formed such a titanic world. In fact, the planet is about 1% the mass of its star, just like Jupiter, and receives about as much light from its star as Jupiter does. It is not even the first system of its type to have been found in orbit around an object like this. In 2021, a 10 Jupiter-mass planet was found in an even larger circumbinary orbit around the double B-type star B Centauri. So B-type stars might just be as amenable to planetary systems as their smaller cousins, just on a grander scale. Don't be too happy for Mu-2 Scorpii b. B-type stars have lifespans of just 40 million years, and when Mu-2 Scorpii goes, it's going in style. Chances are the supernova will take the hapless planet with it. It's also possible it could escape, cast into the void to wander the depths of the galaxy alone. Ancient eyes uncovered. Astronomy is the oldest of sciences, and 2022 was notable from the revelation of astronomical discoveries from ages past. If you follow my channel, you will already know about the discovery of the oral record of a total solar eclipse among the Ainu people in northern Japan. But that was only the closest stop on a very long road. Our next stop on the temporal train takes us all the way to 1054. In recorded history, our race has been gifted with 7 naked-eye supernovae, the most recent of which occurred in 1577 and 1604, and were studied by Tycho Brahe and Johannes Kepler, respectively. But while our records for that pair are fairly comprehensive, records for earlier events are relatively scant, particularly in the so-called Western world. The supernova of 1054, which we today call the Crab Nebula, was recorded assiduously by the Chinese, much later by the Japanese, and by the Arab Christian theologian Ibn Butlan. The Anasazi may have recorded it in their petroglyphs, but of Western records, there is not a whit. Until, perhaps, this June, when a team of researchers for the strikingly named Journal of Science and Theology noticed a strange variation on a Byzantine coin. The term Byzantine Empire is a modern invention. They were the surviving eastern half of the Roman Empire and described themselves as such until their final conquest by the Ottomans in 1453. The emperor at the time was named Constantine IX, whose coins featured a star over his head. But this particular variation, minted specifically in 1054, shows two stars on either side. Could this extra star represent the additional star that appeared in the sky? Well, copies of the coin made throughout that year show the additional star as progressively smaller, just as a supernova would appear over time. Why were Western records so hesitant to record the Nova Stella? Some speculate it might have been due to the dominance of the doctrine of Aristotle, who claimed that change and decay were impossible in the heavens. Since challenging Aristotle was uncomfortably close to challenging the Church, astronomers of the time likely thought it wasn't worth the risk. And this wasn't the only Roman, record to shed light on the skies of the past. In September, a team of Japanese researchers combed through Byzantine records of total solar eclipses from the 4th to the 9th centuries AD, a time when eclipse records in that part of the world are particularly sparse. While direct observations were thin on the ground, they could be reconstructed in quotations and translations by later scholars. In the end, the team were able to establish precise total solar eclipse records for the years 346, 418, 484, 601, and 693. Now here's the interesting bit. The records don't match mathematical models. Of all the astronomical phenomena we could plot into the past, you'd think the easiest would be solar eclipses. But you'd be wrong. The eclipse of 418, for instance, was recorded as bringing darkness to Constantinople so complete that stars appeared in the sky. Yet models suggest Constantinople was outside the path of totality at the time. What's going on? Well, the Earth doesn't always rotate at the same speed. Sometimes it's a few seconds slower, sometimes it's a few seconds faster. Over time, the difference adds up, and as far back as the 5th century, it was as much as 3 hours. This is not something we could have learnt from astronomy. Only history could tell us. It is often said that the lives of stars are immaterial on human timescales. To be fair, for most things, that is true. Even the shortest-lived stars have lifespans approaching 10 million years, a time longer than separates us from chimpanzees. The panic over the red supergiant star Betelgeuse fading in 2019 was an illustration of this. If Betelgeuse's 8.5 million year lifespan were equal to a human's, then a single day would equal 300 years. Obviously, Betelgeuse will explode one day, but the chances of it being in our time are minute. And yet, humanity has seen change among the stars. Edmund Halley used ancient Greek records to show that the positions of some of the brightest stars had changed over time. And this year, a team of astronomers at the Jena Observatory in Germany examined Roman and Chinese records from within a century of the birth of Christ to obtain clear descriptions of the color of, yes, Betelgeuse. Gaius Julius Hyginus, a Palatine librarian during the time of Caesar Augustus, described Betelgeuse as often being confused with Saturn, which should surprise anyone who's seen Saturn lately. A century earlier, Sima Qian, a senior archivist in the Western Han Dynasty, described Betelgeuse as yellow. The Almagest, the most complete star catalogue from the ancient world, lists several red stars, but Betelgeuse is not among them. But, come 1,000 years, and astronomers were reliably describing Betelgeuse as very much red. This suggests that Betelgeuse only recently entered its red giant phase, and so is unlikely to detonate in the foreseeable future. Antares, on the other hand, has always been described as red, and it is much bigger than Betelgeuse. The farthest stop on our train takes us to the early 10th century BC and ancient China of the Zhou dynasty. The Bamboo Annals, a historical record composed sometime in the 4th century BC, record a 5-colored light observed in the northern sky sometime in the reign of King Zhou. While the bamboo annals are not considered the most reliable source, they are a copy of a now lost original and were frequently lost themselves. This year, a chart of Earth's magnetic field showed that it was tilted 15 degrees further toward China at that time, which would make this five-colored light the earliest known record of an aurora borealis. Europa Universalis. It's happening! It's finally happening! Sorry if I'm a bit giddy, but I've only been waiting for this mission for 30 years. In December, NASA's Europa Clipper mission, which lacks a proper name despite launching in less than 20 months, received its latest organ, a mass spectrometer that will effectively act as its nose, sniffing Europa's atmosphere for trace gases. But its real goal, the one that everyone is waiting for, is to use ice-penetrating radar to map the subsurface of Europa's ice shell, finally directly observing its still unconfirmed ocean. Once the subsurface is mapped, the way is open for a lander to sample it for biosignatures. As for that much-anticipated diver, we don't have the technology yet, but it's coming. Given the build-up to October of next year, it's not surprising that Europa was top of mind for planetary scientists in 2022. In March, a team at the University of Texas at Austin created a model that elaborated on an idea I mentioned in my video on Europa, that oxygen trapped in peroxides at the surface could be delivered to the ocean below it through subduction of surface materials. The model presupposed a current hypothesis, that Europa's chaos terrains, that is, broken, jumbled regions that resemble unfinished puzzles, are caused by subsurface ice melt, which creates a brine. The model suggested that to create terrain such as that, the brine will have to flow in a porosity wave, in which ice expands to allow the water to flow and then contracts behind it, essentially a real-life version of the ball of water traveling down a cartoon water hose. This transport is very efficient, with 86% of surface oxygen reaching the depths, but the actual level of oxygen in Europa's ocean is still unknown. Estimates vary by a factor of 10,000. In December, another team at Austin suggested that comet impacts, which contain vast amounts of organic materials, could create huge downwellings of meltwater, which would sink through the shell, bringing it to the ocean. Previous models had suggested that for impacts to deliver such material to Europa's ocean, they would have to break entirely through the ice, but this model showed that they need only reach halfway. On the other hand, if meltwater is heavy enough to sink, that suggests it is unlikely to be the source of chaos terrain, as it would not remain near the surface. In April, a team conducting an utterly earthbound study on the imperiled ice sheet of Greenland caught a lecture on Europa and couldn't help but notice something familiar. A series of M-shaped crests that appeared to be scaled-up versions of ridges on Greenland's ice cap. Using ground-penetrating radar, the team had realized that these chevrons were created when pockets of subsurface water froze and then fractured 30 meters below. The crests on Europa are over 300 meters high. If the scale holds true, that would mean that the water pockets might exist as little as 5 kilometers below the surface. That may seem like a joke, but Europa's crust is believed to be about 20 kilometers thick, so any closer is an improvement. These shallow pockets would likely receive organic material from impacts or Jupiter's other moons, providing a method for complex chemistry to reach Europa's ocean. In May, a team of researchers at UC Berkeley and the University of Washington conducted experiments with water at various salinities and pressures to test how far the frigid, high-pressure environments of the solar system's icy moons could support life. Employing 5 different forms of salt and pressures up to 3,000 atmospheres, the team found that water could potentially remain liquid at temperatures as low as minus 35 degrees Celsius. Yet more reason to be thrilled at the thought of what lies below Europa's ice. In June, a team at the Southwest Research Institute observed Europa with the Hubble Space Telescope. They found that Io, Europa's volcanic innermost sibling, spews sulfur dioxide from its eternally erupting volcanoes, which is then caught in Jupiter's magnetic field and dumped onto Europa's trailing hemisphere. That is, the famous one. While this may not have been particularly surprising, it nonetheless is yet another feather in Europa's biogenic cap, as sulfur is a vital component for proteins. Another vital element for life, and one which may be surprisingly rare on an interstellar scale, is phosphorus. It forms components of DNA, RNA, cell membranes, and of course our bones. Initially, it was believed that another potential ocean moon, Saturn's Enceladus, might be relatively poor in phosphorus, but models of the geochemistry of its seafloor suggest that phosphorus could be unusually soluble in Enceladus's water. What is true for Enceladus is likely true for Europa. It seems that all the necessary tools for life may be present in this one small moon. In November, a team at Johns Hopkins used terrestrial plate tectonics as a model for Europa's crustal motions. Surprisingly, they found that portions of Europa could be explained as analogous to Earth's tectonic plates, broken, vast fragments moving up to 100 kilometers. However, unlike on Earth, these plates did not comprise the entire surface. They also found that, unlike plate activity on Earth, Europan tectonics is intermittent, with no sign of it happening today. But it does suggest that the water magma below Europa's crust is energetic enough to power it. All in all, Europa remains its tantalizing, increasingly hospitable-seeming self. The Europa Clipper is expected to meet up with the Moon in 2030. Here's hoping that until that day, it will continue to keep us entertained. And that's the end of part 1. If you can't wait, the full 70-minute audio is available for my patrons on Patreon, which you can join for $1 a month. If that's not an option for you right now, you can help just by liking, commenting, subscribing, and even chatting about me with your friends. The favor of the almighty algorithm is hard to gain. With your help, I'm slowly doing it. Stay curious, fellow seekers.